Okay, it is 4 o'clock, so we shall get started. We're very pleased to welcome our speaker today, who is a fellow CSU professor up to visit us from San Francisco. So it's always great to have someone from inside the CSU system. While there may be many campuses, it's one of those things that's great to have these connectivities between various locations. The other connection we have is that the background of Professor Nuis's work overlaps with a lot of the work that is conducted here at Sonoma State and some of the experience we have in the department. So I think there's some great overlap between that and some of the projects that we can offer. So with that said, let's give a very warm welcome to Professor Nuis.
Well, thanks for inviting me. I think this is a really beautiful campus. It's very nice to see green campus. Yeah.
Can I ask you to speak up a little bit?
Oh, I see it. Yeah. I'll try. Well, so I'll try to be in this talk. I'll try to be kind of informal. So I'll try to convey the excitement of the research field currently in this direction. So in this talk, what I'll talk about this new class of materials called two-dimensional atomic layered crystal materials. All right. So these materials is not like we are using that for a long time without knowing it. Like for example, in graphite in your pencil, how do you write on a paper? Because you have all those, in graphite, you have all those layered, one atom thick layered materials. They are just attached to the next one just by van der Waals force, which is very weak. And then when you write it, those layers getting glided through or getting on top of the page, so that's why you can write on a graphite. All right? And then, and interestingly, these materials, though one atom thick, but now people can make very, very large size. And then in this talk, I'll show you that, what is the excitement there. So for example, this is, as I told you, that carbon atom forming in your graphite is like you have a benzene ring attached to each other making a large shape. All right? And then, and you can see this is a scanning electron microscope image of one atom thick layered material. So, and you can see this surviving in air, and so that tells you the mechanical strength of the material. All right? So not only that, you also recently, we know that there are other materials that is also you can have one atom thick and with different optical, different physical properties. So some of them can be metal, some of them can be semiconductors. So I hope I'll be able to convey the excitement at the end of the talk. So let's see what is the dimension I'm talking about. All right, so as you know, the earth size is 10 to the power 16 nanometer. Right? And then you go by 10 to the power 9, 10 to the power 8, you get to the golf ball. Not golf, I'm sorry, baseball. Then if you go more, 10,000 nanometer or 10 micron is your hair, the width of your hair. And then if you go more, it's a virus, right? 100 nanometer, you get to that scale. And the materials we talk about less than a nanometer thick. For graphene, one atom is only 0.35 angstrom. For monolayer MOS2 is 0.7 nanometer or 7 angstrom. So brief history, I want to talk about that graphite. We know that almost 4,000 years old, people were using graphite to decorate pottery. All right? And that's a three-dimensional carbon-based materials. And then it took almost 6,000 years to get zero-dimensional materials that was invented in Rice University by the smallest group they call carbon-60 or fullerene material, where you have carbon-60 arranged in a hexagonal and pentagonal making a big sphere. And then we got around 1991, we got one-dimensional carbon nanotube from Japan by Izima's group. And then it took a long time. People realized because they got zero-dimensional, one-dimensional, three-dimensional. So the missing is two-dimensional, right? The reason was that because there was lots of theory papers there that were saying because of the surface energy of the two-dimensional carbon sheet and the substrate will make it crumple. You will never be able to get a monolayer sheet of carbon-based material. So that's why lots of people did not try it, because theoretically it was not possible. But there was a person I'll talk about more that he did not look much on the theory paper. Just give a try. All right. So in 2004, that paper came out from Manchester. Is a two-dimensional carbon-based atoms called graphene. And then in 2010, people realized it's not graphene because it's open. It's give you techniques to really study lots of other materials. That's a layer material. So one of them is molysulfide, and there is another one called boron nitride. We are using that without knowing it for a long time in the cosmetic industry, in lipstick, literally. And then you have thermoelectric materials in your heat sink, or when you cool down something by using applied bias. You can have these other layer materials. So, for example, molysulfide. If you go to AutoZone, you can buy this molylube. Actually, nothing but this layered material. Because you see, you can have a low friction because it's a layered material. So you can very easily take from layer by layer, so the friction is very low. All right, so the Nobel Prize came in 1996 for this carbon nanotube, and then came, came for buckyball or fullerene for the zero-dimensional, and then came the 2010 for graphene. So, and then we don't know in the future what is going to happen. All right? So I want to talk about, this is the person, Andre Geim, who actually built up this field. And this is because of his out-of-box thinking. All right? So he's a Russian-born physicist, got his PhD from Moscow State or Moscow Institute of Physics and Technology. And then he did a couple of postdocs in UK. And because he did really nice work there, he got his first faculty position in Netherlands. All right? So he got graphene, or some of the experiment I'll talk about, that because of his all kind of crazy ideas or out-of-box thinking. All right? So one of the experiment, he literally said Friday night experiment for testing crazy ideas. So I would recommend you read this paper. This is a very easy reading. This is not about physics, it's more about the story behind the science. Okay? So one of the crazy ideas is levitating frog. So people knew that for a long time, when you have water going through the copper pipe, you have this scale build up over time. All right? And that when you put the magnet next to the pipe, you don't see the scale. All those formation of those scales there, it's like you can see no scaling. So, and they call it magnetic water. So people, there was no clear explanation. So Andre Geim was a professor was a faculty at NIMS at Redbound University. But that university is famous for a high power magnet. That's a room temperature magnet. You can go to 20 Tesla. And so he was thinking, so one Friday evening, he did this crazy experiment. He dumped a bucket of water into the 20 Tesla at room temperature. And you can see that the water droplet hanging in the water, in the magnetic field. All right? So the physics behind is not very complicated. It comes from the diamagnetism property of the atom. When you have a magnetic field, your electron orbital motion changes, that creates a magnetic moment opposite to the magnetic field you apply. So he explained that. In fact, there was a Michael Berry. They both was the theory guy, and Geim was the experimental guy. And because of that, they got the Ig Nobel Prize. So Geim is the only person who got both Nobel and Ig Nobel Prize. Ig Nobel Prize is the prize that's given by Harvard and MIT that makes you laugh at the beginning somewhat, but that also makes you think at the end. All right? So, but the media attention got when he put the frog in the magnetic field, the frog also levitating because of the diamagnetic property of the atom. So another crazy experiment he did is the gecko tap. You know that gecko is kind of walls. So if you look the optical image of that, you can see all these pillar things there. All right. So what he did is he microfabricated these kind of structures, and he was able to put a toy hanging from the wall. All right. So that's also out of thinking. It comes from a Friday night crazy experiment, and opened a new direction in thinking and doing research. Okay. So now I'll talk about how he comes to the graphene. So he had this research on. He was interested to metallic electronics, because we know that all this electronics in your chip is made of semiconductors, because you can make transistor using semiconductors, not metals. The reason is that when you apply the electric field, you cannot change the property of a metal, because your electric field will be because of the skin depth, will not be able to get further penetrated into the metal. All right. So, but his idea was, if you have a very, very thin metal, maybe you will be able to get it. All right. So what he did is using high density graphite, and he gave it to the student. Okay, this is the graphite, and we know it's a layered material. Try it, polish it as thin as possible. So the student spent 2 months polishing it and got one flake of graphite. We see thin is the thinnest one. Under a microscope, it looks like around 10 micrometer thickness. All right. So it was like literally, finding flakes, or you are polishing a mountain to get a speck of sand. So there was another person sitting next to it. So they were listening to their discussion, and he was a scanning transmission electron microscope specialist. So if you know the scanning tunneling microscope, what they do, they use graphite for as a standard sample, and they use Scotch tape to remove the clean. So you have a graphite. You start with a graphite, and you have this sample sit in your box. Over time, it will accumulate lots of junk. So what they put a Scotch tape, and they remove the Scotch tape to expose the fresh surface, and that you can have extremely clean surface. But so that STM person, and they were using it from 1960s. So I was saying, so the Scotch tape has lots of flakes in it, and they are very, very thin. Okay? And then he found, when you look under a microscope, it's really, really, you can see very transparent, few nanometer, or even lower, thinner flakes. So there is another group I should mention at the same time. This is Philip Kim's group at Columbia University. They went more rigorous scientific way. What they put they put a graphite on top of a cantilever tip, make a micron size. They call it nano pencil, and they put it on the substrate and slide it. But even using that, they could not go less than 10 nanometer. All right. So, well, so you can see he was saying like. But using Scotch tape, I'll show you some of the results that you can go really one atom thick materials. Okay, so how you started? So you start with a Scotch tape, you put in a graphite flakes on the Scotch tape, and you do like peeling off, layer by layer, because it's nothing but all these layers attached very weakly. And then if you do, sometimes you will see this ugly Scotch tape, but it contains all these flakes in it. What you do that you put that Scotch tape on a substrate, and you very slightly you scratch it, and then you remove the Scotch tape. And what would happen, if you look under a microscope, you will see really very transparent layer, which is actually made of one carbon atom thick. All right. So this is the first graphene electronics that were electron devices using the techniques by the Gimes group, made in Manchester University, and I think that currently this paper has over 40,000 citations. So this is the first paper that came out. All right, that opened the field. Mainly they showed how to isolate the materials, how to make the devices, how you can measure the electrical and all these physical properties of these materials. So now you can ask me, well, you know, those materials in the Scotch tape this scale is 5 micron. What is 5 micron? Less than your hair thickness, right? That is not feasible for application purpose. So what people have developed the recipe, now you can make a really large scale, and they call it chemical vapor deposition system. So what they do, they have a furnace and they have a vacuum system, and they put some metal, like for example, you can put a copper foil. In my lab, we put copper foil, and then we inject methane gas and the hydrogen gas. We ramp up the temperature to 1000 degrees centigrade. The methane breaks up, and methane has carbon in it. Those carbon get into the copper, and then when you cool down very quickly, those carbon get to the surface, make those bonding, and make a graphene large sheet as large as your copper plate. All right? So this is, for example, this is made by a Korean group with Samsung. This is almost 30 inches, and you can, current record is by Sony. I think it is 100 meter long and 2 meter wide. So people can really scale up this technology to make 1 atom thick materials for your technological application. All right? So here are the materials and application. You can think about this large area, large scale CVD graphene, and you have a graphene nanocomposite, some of the like flexible, transparent screen for like on your smartphone screen, or you can have those conductive ink, because graphene is metal, so you can make a conductive ink. Also, you can have a solar cells, or because graphene, if you put a graphene, even the hydrogen atom cannot pass the graphene film. Or you can also have it as a heat dissipation system. You can make composite for aerospace industries, and there are many other applications you can think about. So, well, now you can ask me, well, what can we buy currently, right? Indeed, you can buy several things. You can buy this graphene racket from head.com. What they do, make this metal structure made by graphene because it's very light and robust. All right? And then you can buy this 3D printing system where they make those cartridges made by graphene mixing up with other polymer. You can buy battery. That's the reason. That can recharge up to 15 minutes and cost you around $100. All right? So in the future it's coming, probably you can have a flexible your smartphone, or flexible your wearable technologies, or you can maybe have some medical application. Lots of research groups are working on to use graphene as a DNA sequencing technologies. All right? So any question? Feel free to ask. Yeah.
Yes, if I heard you correctly, you mentioned your gross temperature of like 2,000 degrees Celsius.
No, 1,000.
1,000.
Yeah.
I mean, why is the temperature so high? Is it because the methane has to, keep this kind of temperature to be?
I think it probably needs that high temperature to break up the methane to the carbon and hydrogen.
Is copper crucial in that?
Copper
process?
works as a catalyst. Copper is very crucial. So that's a very good question, because if you put a copper, you can make a monolayer. But you can also put nickel. That will grow multi-layer.
Does the orientation of copper matter?
Orientation?
Does copper have to like?
No, those copper film is polycrystal and
Just
copper
copper,
film,
okay.
but the purity matters.
Okay.
So the copper film in our lab we use 99.99%. So, but other than that, but it is not that important for nickel film somehow. So, all right. Yeah, if you do nickel, you can make many layers. You can make it many layers. So that's the way people control the thickness. Somehow copper is self-terminating. After one layer, it doesn't. Well, people also figured out to make up to bi-layers, but not more than that. Yeah.
I have a couple of naive questions, but I think
Sure.
it'll help fill this in. I think it's won't be just me that finds this interesting.
question. Graphite, is large three-dimensional structures usually, or it's in our pencils. I've heard of the tape as the part of the discovery, the Scotch tape as part of the discovery. Is it something that the amorphous form of it, or I'm
No,
using
you need
that-
they call it HOPG, highly oriented polycrystalline graphene.
Okay.
So
So
if,
there's not like, even when you do small amounts, and what would be the layer of carbon atoms? How many layers thick would pencil markings? Wouldn't it be large, right? I mean, I was trying to look at versus your thin.
but
thin
yeah,
layers.
right. The pencil graphite is high density graphite. So for that one, if you do using Scotch tape, you would not get even if it is there, it's probably less than a micron or
You,
nanometer.
you could get small features of it about a micron thick, and then or a micron across, right? We're talking about-
Even smaller, people don't try a pencil graphite because it's high density. But using HOPZ, you can easily go to 200 micron. In my lab, sometimes you can get 200 micron, which is pretty large for research purpose.
Right. And then I'm just wondering about the purity of it. We're looking for, local deformations or inclusions or, I suppose, whatever the appropriate word is for the, on the atomic scale, individual.
I'll talk about some of those. I'll show you that how the substrate matters.
Thank you.
All right. Yeah. Indeed, the quality of your electronic device definitely depends on your graphene quality. So if you made it using that HOPZ, you get an order of magnitude better quality than you do it by using CVD, but chemical vapor deposition, because the chemical vapor deposition has lots of grain in it. So it's not a large sheet; it's a multiple sheet that's attached to next to it. Yeah.
Can you also say a few more words about one of the transistor the circuit? People first made the graphene, and then they basically made the electrodes. Well, was that graphene also grown on copper or some other substrate?
So, well, even if you do a massive scale, you have to do on copper. And then copper, you can remove it very easily. There are techniques available.
But once you put the electrodes on top of the graphene, isn't it true that the metal is going to penetrate into the copper?
No,
No?
because graphene even cannot pass a hydrogen atom next to it. There's a highly, it blocks everything. Okay. All right, feel free to ask here. Well, I will talk about the electronic properties of graphene. All right, so why is so beautiful or so exciting? So I'll show you, because some of you is just the electronic band. You need to some idea about the electronic band structure, because that will determine the electronic properties. So let's see. So this is just a very close idea how you have all these band forming in a metal. So this is your one atom. And if you can have it from the quantization, you can, for example, you have a 3-layer in energy scale. And you put many of them, and then you form, because of the interaction with them, they form a band. So you have some allowed state, and then you have some forbidden state. All right? And then you can put electron into the system. What will happen is that you will start with the lowest energy, then you start with filling up, filling up, filling up. All right? And that's called your Fermi energies. And this is your allowed band. Okay, so you need to understand, because we are looking at the properties of the materials, which is determine all this band structure, quantum properties of these materials. Okay. Now, so what is graphene? Again, if you look from the top, you have a 6 carbon atom next to each other. Every carbon atom has 3 atoms next to each other. All right. So you can have unit cell, because when you do the calculation or calculation for any materials, you need to have a unit cell, because that will make your life very easy. All right. So one of the unit cell you can have that way, or you can also have it. So this one have it. You can see it's 1 6 1 6 1 6. 1/3 1/3 1/3, and you have 6 of them. So actually 2 atoms in a single unit. Same, you can draw. You don't like this, you can draw this way, you still have 2 atoms in a single crystal. And then you can do the calculation, and it's called tight binding calculation, and then you can come up with these band structures as as I showed you before, but this is a periodic system, so we like to present the band structures in momentum space. That will make your life easier. So here you are seeing the band structures of this carbon and graphene, and you have all, so these are all allowed state, and that these are empty state, it's not allowed state. All right? And then if you blow up, so this is called K point, this is called K prime. If you blow it up, it looks like two cones. All right? And what happens is that when you have some charged particle in a materials, they are called quasi-particle, and they move with some effective mass. And the effective mass depends on the double derivative of this energy versus momentum space. So what would be the effective mass of the system? If you take the double derivative along the line. You take the first derivative, it will be constant. If you take the second derivative, what would be happen? It will be 0. So that means if you plot the energy of this equation, it looks like as some velocity times momentum. That means the particle, quasi-particle in graphene acts as if like it does not have any mass. But you have to remember, that means it acts like a photon. But photon has a speed, but which is 3 times 10 to the power 8. But in this particle, it's a quasi-particle, so it will not have the speed of photon, but it will be closer to the speed of photon. So if you do, it's indeed 300 times smaller than the speed of light. But the physical property is very similar to the light, because if you do the photon energy equation, the energy equation is C times P. If you remember the expression. All right. So that's why people say it's actually massless Dirac fermion. It's massless. It's fancy term. It's just the electrons are feeling like they don't have mass in the system. All right, with this speed. All right. So now we'll talk about the electronic properties. So you have graphene. The way you make. So this is a cartoon where you have a graphene on top. You connected them by gold or electrode or something, and then you have some insulator. So you have a graphene, like this is my graphene. I have some insulator, silicon dioxide, and I put another metal at the bottom. So what I make a capacitor. And by making a capacitor, what happens is that, as you know, in a capacitor you can vary the charge by applying the voltage. And your charge is nothing but N times E. That means you can control the charge or number of electrons in the system just by applying this gate voltage. All right? So that's the way you can, so look at this graph. So you have to understand this now. So here I'm plotting the gate voltage. This gate voltage means like same as if this is nothing but like your transistor like property of your of a sample or your water faucet. What do? You switch the knob, you change the flow rate. Same as here, you change this gate voltage, you can change the properties of the materials. So this is your conductance. You know the conductance, right? Conductance is how the electrons can travel in the system. So the higher the conductance, the better it is. So, and you can see so this is, you remember from the previous slide, you have that cone shape. And you start, when you Fermi energy is ceased, in the middle there is no states available. So your conductance would be lowest. And then you change the bias into negative side, you make it lower the Fermi energy to the hole side. So you are creating lots of hole in the system. And that's why you have a higher conductance. And then also in the other side, by changing the gate voltage in the opposite direction, you move the Fermi energy upward. So you get a symmetric conductance plot like that, right? So if you do the mobility of this simple, mobility is a number which people use to characterize a sample. You have a higher mobility, you have a better sample. So you can see the mobility of a graphene, one atom thin graphene is very, very high. the materials in your computer chip is only 2,000. All right? The best one is available currently is indium antimonide, which is 77,000. All right, so now I'll talk about two experiments that tells you the quality of the material, that is really, really good. What is one of the experiment people study, when you have a very high quality electron moves very smoothly without scattering, what you can see the quantum behavior of the electrons. So one of the properties is the Hall measurement. Do you remember the Hall measurement? In a Hall measurement, you have a slab of materials, you inject electron, and you apply the magnetic field, and that will bend the motion of the charge direction. And that will generate a voltage. And you measure the voltage, and that will, from the voltage, you can calculate the carrier concentration and the quality, or how many carriers are available there. Okay? So you will end up, for the classical case, means there is no quantum mechanical behavior, you will see this kind of linear behavior. All right? For now, on the case of you have very high quality materials, your electron, you apply magnetic field, what will happen? The magnetic field the electron will start to rotate around the magnetic field. So it will create some of those Landau levels. That means if you have a density of states in it, this is your energy, available states, if you apply magnetic field, you will quantize those states. So like that, you can see you will quantize those states, and as you apply the magnetic field, all those states will move up because you will increase the gap, which depends linearly on the magnetic field magnitude. All right? So, and if you measure the resistance, it looks like you will see the states. That's called quantum Hall effect. That is, but you remember in the classical case, what you are supposed to get? Just a linear without step, right? For graphene, you can see it's exactly those steps, right? So that's telling you that really you can see the quantum mechanical behavior in graphene, giving you that is indeed the electrons have very high mobility and moving without mass scattering. All right? By the way, for when the first quantum Hall effect was observed around 80s, I think that the Nobel Prize they got for quantum Hall effect around 86. All right? So not for graphene. That was done by using other materials. Now I'll talk about, as you say, people first studied graphene on SiO2, silicon dioxide, right? But you're putting one atom thick materials, you need to have a very high quality surface. But if you look at SiO2, it looks like it's a ragged surface. And the variation is of the order of 0.4 nanometers, right? So what do you need? You need to improve. So if you put a graphene, what will happen? Graphene will be also sitting on a ragged surface, and the electron will fill electron will feel lots of resistance coming from the materials. All right? So what we found, well, you have a graphene here, you have a brother here, it's called boron nitride. It's the exactly same structures. The lattice, this is your lattice constant, that is the number of the separation between them is very close to this boron nitride. And this is also layered material. So you can have atom flat substrate. So that is what they did. So what they did is that, so this is the next advancement they did. So they have a graphene here, and they prepare a microscope slide with boron nitride. And what they did, so and they put and they under the microscope, think about it, all these materials is few micron. They align the samples under microscope and put graphene on top of boron nitride. All right? And this is a quite challenging job because you have to do everything perfectly to do that. And then you can see this is your boron nitride, and on top of you have graphene. And if you have that, and what you are looking at here is the surface roughness. So this is your surface roughness in silicon dioxide, and when you put it on top of boron nitride, it shrinks by a magnitude. Okay? So because now you have a better quality graphene, so you can see even more quantum mechanical behavior properties. They call it fractional quantum Hall effect. So which was not possible to see when you have a graphene on silicon dioxide. So you can see that you have all these fractional numbers. All right? So I just wanted to, I hope that answered your question, that indeed surface roughness is very important for this sample. Okay, so now I'll talk about the other things. So now I know how to make one materials on top of other, right? So what happens is that, what happens if I do the aligning of two graphenes on top of each other? All right, you can change the physical properties of the band structures of these material, just make it so with the preferred orientation. So for example, here is the image. You can see you have one graphene and the other graphene on top is moving. You see those structures are appearing. So you have a carbon atom with hexagonal symmetry, and then depending on the angle, you create another structures on top, right? That's called moire pattern. All right. So this is, if you in a slower slide, you can slow. So you have this graphene. If you put a certain angle, you can see the angle. You can have graphene here. You can also have this hexagonal pattern. All right, and so this is, so you are creating a superlattice with another, right? You have a hexagonal and then putting another hexagonal with larger lattice constant. So what would happen is that, indeed, you remember I showed you at the beginning that band structures for pure graphene is a conic shape. Now you create another hexagonal. What happens is that you create more conic shape, but at different energy level, right? And then you can see, before I had only one structures. Now I create other structures in the conductance as I changes the carrier density. Yeah.
So experimentally speaking, how can you align the two layers so precisely?
That's the magic of their hand. They can do that because that's a very good point. People have figured out that you have this breaking point of the graphene and you have another breaking point of the graphene. They follow a certain angular distribution. So either they can have zigzag or they can have armchair shape. So you can, if you do those angle orientation of those edges, you can come to that angle. All right. Very nice question. So, so you can see that indeed you can change the electric, not only you can change the band structures of the materials by angular orientation of the system, right? So recent work, this just came out last month. There is at 1.1 degree, they call it magic angle. When you have a magic angle, what happens is that the band structures get flattened. Like here, you have a band structures flattened at the zero. What happens is that you can obtain this new type of superconductivity. So that is, you can see at theta when 1.5 degree, when go to low temperatures, boom, you go to superconductivity. And this is your current data as a function of voltage. You can see all this superconducting behavior. Right? Well, so now I'll talk about a little bit about how what kind of work we do in the lab. Is one of the work we did is at the beginning, what is really causing the scattering in these materials? All right. So you have this flat land, and in the flat land you will have all these charges in the system, and because if you have a charge in the system, they will create what? It's a Coulomb's law. Coulomb's law goes to infinity. So it's a long-range scattering. Or you can have defects in the system, so you can have a vacancies in the graphene. that is called short range scattering. Means it does not, the effect does not go very far. All right? Another one can be ripple. If you have a ripple in the system, that also introduce scattering in your system. So what we did is that we did some control experiment. We created suspended graphene monolayer material, suspended graphene samples in dielectric liquid. Because every liquid has dielectric property. So you can have a sample in a dielectric environment, you can flush the liquid, put a new dielectric materials. That means you can tune the dielectric constant by using, so as you all remember, this is a Coulomb's law. And Coulomb's law has this dielectric constant. So our goal was to vary this dielectric constant and see, this is your scattering strength. If I increase it very, very large, what would happen? This scattering potential will go down. And then my electron should see smaller scattering. So that is what we did. We made a graphene devices suspended in liquid, and we we flush the liquid and measure the electrical properties, put a new liquid and measure it again. And then what we did, we showed you, indeed, when you have a higher dielectric constant, your graphene gets better. So that tells you that indeed it is the long range Coulomb scattering that is determining the electrical properties. So the fab is, you start with a graphene on a silicon dioxide, then we have a way to remove the substrate underneath it, and then you study this device, put all the electrodes, and put the whole things in a magnetic field, and measure the electrical properties. So this is a scanning electron microscope of this is a Hall bar shaped graphene device in vacuum. All right. So very quickly, again we have this. So we vary we have varied the liquid from, because we vary the hexane, toluene, and anisole, because all these three liquids are non-polar solvent. What does it mean? Meaning it does not have any stray ion in it. It's a very pure solvent, but it has a different dielectric environment. All right? And then using that, and you can see this is at the beginning of this, and then when you put it in hexane, it's improved a lot. So this is a conductance. The conductance getting higher means my sample is getting better. But is it one sample? Is all I'm doing is changing the environment next to it. And then if I do more in toluene, which has a dielectric constant 2.3, it's getting even better. Even if I do anisole, which is around 4.3, it's even better. So that was the experiment we did to resolve the controversy we had at that time what is the scattering mechanism. So what is the application of that? Well, you can think about so one of the applications we did, we extend that experiment further, because graphene is the most sensitive charged material. So what we did, we make a graphene transistor, we put a microfluidic channel on top, and we flow the liquid on top of it. And study, can you measure the flow velocity? Indeed you can. We were able to, sensitivity of our devices was 70 nanoliter per minute. And then we did sensitivity, not only the flow velocity, you can also measure the ionic strength in the material. All right? So it has a dual sensing properties of this sample. All right? Now, so we're done with now, graphene is metal. We all agree on that, right? It's a metal because graphene is not a semiconductor, right? So now we'll talk about what graphene has opened up this, graphene field has opened up these techniques to study other materials. So one of the materials is called polysulfide, which is a direct band gap semiconductor when it's a monolayer. So what does I mean by that? I mean that, so semiconductor can have two types of band gaps. One is the direct band gap, one is the indirect band gap. So indirect band gap, again, this is your conduction band, and this is your valence band, and the bottom of this conduction band sit exactly on top of the valence band. So what happens is that if you shine that with light, light has a very tiny momentum. It will generate an electron, put an electron here, put a hole there. It's a very efficient process. But on the other hand, if you have an indirect band gap, they sit at two different positions. So you need to, because your momentum needs to be conserved, so light needs to involve phonon to transfer this process, to make this, when you hit the light, when you hit the sample with light, you create it. So to create an electron here, hole here, you need to have it's a three particle system. So it's a very, that's why you cannot buy a laser pointer that's made with silicon, because silicon is an indirect band gap. On the other hand, this is a aluminum gallium arsenide, the glazing medium here, because it's a direct band gap semiconductor. So this is molysulfide, where in molysulfide you have a molybdenum in the middle and you have a sulfur on the outside. So they call it a trigonal cell, and it has some crystal symmetry. Because of the crystal symmetry, what happens is that this is the band gap looks like now for a monolayer. And you can see, indeed, this is a direct band gap semiconductors at the monolayer level with this at the K point. All right? And if you look it more, because it's also hexagonal, so you will have this band at 6 different points in the hexagon. And it also has a very strong spin orbit interaction. Means that your valence band split up at here, which is of the order of 160 MeV, so you can observe it even at room temperature. Okay? Not only that, it also has these quantum properties called values, K and minus K. And note that in this minus K point, the blue is sitting on top, on this one, blue is sitting at the bottom. So the electron at this value cannot just travel to here because it's sitting at the bottom. So you will have a way to create carriers, electrons, with certain this quantum behavior. All you need to do, put some angular momentum so that your electron can transfer to here, but it does not talk. So when you put the way we do is you can polarize the light this way, and the polarization has angular momentum +1. This way, angular momentum -1, and you can selectively generate these polarized carrier. They call it valley polarization. So that's a big potential for a new type of electronics called valley photonics. All right. So again, it's a direct band gap at the monolayer level, and then you have a valley degrees of freedom. So you can see here that when you have this kind of circular motion, you are talking onto only the K point. When it's going the other direction, you are talking only the K prime. So this is your optics. So what happened? This is your MOS2. Do you see? There is a monolayer MOS2. Probably it's hard to see from there. This is your band gap. You heat it with light. You create an electron and hole. And what happens? You create an electron hole. Your electron is here. Hole is here. There is nothing here. There is nothing here. So what would happen? You have a very strong Coulomb interaction. Because of that, what you will create a hydrogen-like bound state called exciton. All right? And that exciton has the binding energies, and these and then those exciton, the exciton will collapse, and new light will come out. All right? So this is the fluorescence image. That means I'm heating this sample with green light and measuring what is the light coming out. And you can see this is a room temperature measurement. I can see the epoch when the transition happened from here I can also see the B peak when the transition happening from the bottom one. All right? So not only that, because it's a very strong interaction, I can also create three-body system called trion that can have a 2 electron, 1 holes, 1 electron, 2 holes. The electrical properties is a very little different than graphene because you have this band gap. When your Fermi energy sits in the middle, there is no current going through the system, so your conductance is 0. As when your Fermi energy touches this bottom, your current starts to rise. So this is very similar to your transistor in your silicon. Yeah.
I was just wondering on the previous slide, I was thinking about new problems with, particle in a box, quantum uncertainty for the lifetimes of these excited states in the hydrogen atom. What are the lifetimes? I mean, this looks like another problem that could.
No, the excitons has lifetime of the order of 100 picosecond to nanosecond, depends on what is the environment. Trion has even shorter lifetime.
Yeah. You could generate the same thing maybe by.
What is the same thing?
By a lifetime from delta E, delta T, and H bar. I mean,
Yeah, it's well, I think it's a very similar behavior.
It's interesting to do on a.
Right. Maybe.
Okay.
All right. So the electrical properties here is your MOS2 connected by 2 gold electrodes, and this is a very transistor-like behavior, very similar to your silicon. And then, as you have already discussed, the graphene looks like very different, right? So what is the problem of the graphene? Because graphene does not work as a switch. Here you can see, right? You can completely turn it off. Here you cannot turn it off. You go to change the voltage, so you change the faucet this way, water flows, go other way, water flows. So you cannot make transistor out of graphene, but you can make transistor out of MOS2. All right, yeah.
Isn't it true your mobility is only 1 centimeter squared per volt per second?
People has gone to 100 now,
Okay.
100 centimeter. I think recently they have even seen quantum Hall effect behavior in MOS2. So people are improving, but it's a slow, yeah.
Okay.
It's only 8 years now, so working on figuring out, yeah. One of the reasons is that MOS2 has lots of defects in it too. It's very hard to make high quality compared to graphene. Well, again, people have figured out to make a large scale, wafer scale MOS2, because if you want to make it as a device, you need to make it as a larger scale, wafer scale, 6 inches wafer scale. So very similar to techniques, they use one is the precursor, they use chalcogen, another one they use transition metal and put any kind of substrate, ramp it up to around 800 degrees centigrade, and you will get MOS2 flakes like that. So this is one of the samples in our lab, but you can see this is 50 micron. So we don't work on wafer scale growth, but people have already demonstrated results that wafer scale growth of these materials. All right. So very quickly, that one of the study we do in the lab is we study the photocurrent. Means you heat it with different color of photon and see what kind of light coming or what kind of current coming out. And from there you can tell the electronic band structures of the quasi-particle behavior of these properties. So we have a monochromator which put through a monochromator that can selectively select photon color from red to all the way to green or UV. And then we measure it, what is the property. So this is one of the photocurrent as a function of the color. And you can see this is in EV, so this is UV to all the way to red color. And you can see all these peaks coming out is very similar to when you have this transition happening. You see a peak there. You can see when you see big peaks when this transition happens, and then you can also measure. And this is happen when you have this transition directly from here to there. If you subtract that two value, you can directly measure the binding energies of this exciton. You know the binding energy of hydrogen. What is that? 13.6 eV. This is around 500 MeV. all right, which is pretty large. So you can see all these effects even at room temperature. All right. So, so now I'll very quickly show you that because indeed this is a one atom thick material, and you can control this luminescence property of this material just by generating different carrier number in the system. All right. So you can see this is a device. I'm shining this with light, green light. I'm measuring what kind of light coming out. All I'm changing this gate voltage. If I do that, you can see my sample was very bright at the beginning. As I'm changing the gate voltage, it's becoming dimmer. You can have a movie, you can see I'm changing this intensity level just by changing the carrier density level in the system. And so you can think about this, modulating this behavior. All right? So now, where's the field going, right? Currently, there are almost 200 materials of this family. So, so some of them can be graphene, some of them I showed you chalcogenide semiconductors, then can be oxide, there can be magnetic materials, there can be ferroelectrics, and not only that, you can put one on top of each other. So what do you have? You have infinite possibilities to make the complex devices. You can make whatever properties you want and make the devices to get the properties, right? So, so again, you can see this is like, as I told you, that you can have this, they call it van der Waals heterostructure because the thing that is holding is the van der Waals force, right? So this is, you can have many different, like for example, boron nitride, MOS2, boron nitride, graphene, boron nitride. So people figured out to make many layers to stack on top of each other, right? So this is in one of our lab. In our lab, you can see we put two different semiconductors on top of each other. Not only that, nature makes these materials which has two different semiconductors, one alternative way. That's called frankite. There is called frankite. This is your lead sulfur. This is your semiconductor, and you have another type of semiconductor. Then this one repeats again, and nature made that. All right. So this is one of our research recently. We work on that, and you can see the layered structures in SEM, right? So, but it is a nature-made two semiconductors alternative. All right. So again. So we make devices in the lab, and we study the optical properties and photocurrent behavior. So, what I wanted in this talk to give you the excitement in the field and where is it going. So the possibility is kind of endless. You can just think about what materials you want, what kind of stacking you want, and then you can. So lots of new exciting physics has started to coming out. One I have shown you, the superconductivity. People have studied other behavior. So people just realizing, it's not that very old field. It just started around 2004 with graphene. Then new materials start to come around 2010. More things have started coming out. People have mastered on fabricating complex devices, high quality devices. So. And yeah, this is my group at SF State, and thanks for the time.
As it's 5 o'clock, I know many of you who are here for extra credit have other things to attend. So if you're here for extra credit, you're welcome to depart. Otherwise, those of us who remain behind will take some questions for the speaker. So if you don't have questions for the speaker.
Yeah.
Just naive idea. I mean, when you had the rotation, right? I mean, we were talking about the permeability, and I just want to know, is there thoughts of use as kind of molecular sieves, or are you basically saying nothing is it's impermeable to most everything? Are any of these structures have any interesting sizes? Are there any interesting ways to use this to?
Well, the guy goes at Manchester University. They're working on the sealing property of this fuel layer graphite, and they showed that indeed you can control them, different types of molecules you can do. You can use as a filter. You can also protect, isolate purifying liquids by applying that. Also, people are working on this, as I told you, that DNA sequencing by making a tiny hole and passing the DNA and measuring the electrical property. So, the engineering, yeah, it's a lots of work going on. Lots of people are trying all different ways. But the good thing about superconductivity is just because it's to give you you can control the superconducting behavior, and you can understand why the superconductivity happening for some materials. So this is a new playing field that just appeared when you control this. Band structures just by changing this angle. Yeah.
This is great. I mean, I feel like this is a wonderful material engineering. So one thing that kind of surprised me was when you showed the photoelectric spectrum of the disulfide, there was really no peak close to that 2.5 to 2.6 electrovolts, which was the band gap. So I was kind of wondering, is it because of the quality of the material you really don't have any transition, from the top or the bottom to the other side of the band structure?
So I didn't, because that's a very good question, because the reason is that I didn't talk about that, there's this new band structures appear because you have a conduction band and you have valence band, they are flat. So what happens is that you have an optical density which is also flat. So you have a singularity in the optical density of state. And that's called Van Hove singularity. And that's why you can see that C peak appears there, which is very next to this transition, but C peak is much larger than A peak.
Right.
That's telling you that C peak absorbs almost 40% of light. And that C peak is totally coming from this singularity of this density of states. And that's kind of probably is trying to overwhelm the transition, direct transition you were talking about around 2.5 eV.
Yeah, but it didn't have that 1.9 EV peak, and I always suspect this is due to the defects in the band
No.
gap. It's not. It's
No,
definitely from
this that I showed you, those are for suspended samples, annealed suspended sample in vacuum. So the quality of this sample is very, very good. Even if you have a CVD sample, you put it in a substrate which is not optically active, you see A and B, you don't see other. So it looks like the exciton behavior, because the Coulomb interaction is so strong, you shine this light, right away you form those excitons.
Right. The exciton, usually they have an energy maybe 100 or 150, mil EV below the band gap. But here we're talking about 1.9 versus 2.6, so it's
Right.
really huge.
Yeah, it's around
Yeah.
so it's around 600 MeV.
Right.
Which is very strongly bound. The only reason is that you don't have any materials on the top or on the bottom. So the Coulomb interaction is very, very strong. So that's something, it's a very interesting material for optical devices. Yeah.
Yeah, thank you for the fascinating talk and the idea of getting the Moiré effect through the angle tuning and changing the properties that way. That's really remarkable. But one thing about these materials like the HOPG, it doesn't conduct heat this way. It does conduct heat that way. I find that fascinating. And is it BISCO, the thermoelectric material, bismuth, indium? So when you twist the material or misalign the two fringes, what happens to the conduction is usually given along the plane.
Correct.
So it doesn't conduct at all outside the plane, or the two stacks don't connect.
So people have studied it, they try to study the two layers on top of each other. So there's no conduction this way. It's mostly conduction this way.
But when you twist it, is there?
No, it's because of the interaction of those two layers, you modify the band structures. But electron is still remaining in the same plane. They now see two different periodic potential.
Well, I'm thinking about tunable gratings or
Uh-huh.
tunable filters through the forbidden way, or through the wide way. So when you make those changes to the spacings, it looked like larger pathways through it were opening up through the two sheets.
Mhm.
So no, our conduction through them, the
Well, this is,
forbidden way is now allowed.
yeah, I think, so, I don't know the answer for that. So I think the people have just started to realize to do this angle, preferred angle orientation, and more results are coming in, so.
And what do you see as the applications?
Oh, for that one, you know, the first of all, the application would be to understand the superconductivity. People have studied all these materials, but there is still lacking understanding of superconductivity. So that would be one of
That's the
that.
big one.
That's the big one, that's most exciting one.
But what about microphones or phonon, electron tuning instruments?
Well, I showed you that for those, you don't need wide pattern. Even a single layer graphene would do the job. I think soon you will buy those Galaxy skin that you can bend it, or you can wear some shards with graphene on it. So those you don't need a complex structure. So those, when you just apply the electrical conduction.
Yeah, before we finish, just a quick note that our speaker is staying for dinner if you'd like to join us. Otherwise, let's thank our speaker again.